Today we will continue with the 2D finite element problems, and in the last class we had derived this relationship, that is the total potential energy is given by half of Q transpose KQ minus Q transpose F when we are using 3 noded constant strain triangular elements. And for deriving this, we had said that if we have an element 1, 2, 3 and there are some tractive forces acting at the edge 2, 3, then the total tractive force acting on this edge can be split equally between the nodes 2 and 3. Okay, the total tractive force acting in the x direction will be split equally between these two, that is between the nodes 2 and 3, and similarly the total tractive force in the y direction will also be split equally between the nodes 2 and 3. Again, similarly the body forces that are there, they will also be split equally between the 3 nodes. Okay, so we will have some body forces acting effectively at these 3 nodes. Okay, that is the total body force acting will be split equally between the 3 nodes, and this way we can compute the global force matrix by including the forces on each of these 3 nodes plus all the point loads at each node. That way we can compute the total or the global force matrix, and the stiffness matrix that can be computed by finding the local stiffness matrices for each of the elements, which will be 6 cross 6 matrices, and then we can compute a global stiffness matrix. Let's take a small example of how we can compute the matrices in this case. The process is going to be absolutely similar to the process for one dimensional elements. So if we take 2 elements like this, okay, that means this is node 1, 2, let us say I call this 3 and this is 4, and let us say I call this as element number 1 and this as element number 2. I just have a plate with 2 triangular elements. Okay, it's a very simple situation, and let us say I consider that and here okay, and there is some load acting, let us say at node 2. So this is my node number 1. So my element 1 is defined between nodes 1, 2 and 4, and element 2 is defined between nodes 2, 3 and 4. Okay, or I can take any sequence 2, 3, 4 or 3, 4, 2, that does not make a difference. Okay, if I consider the first element and I write the B matrix for the first element, okay, that is B for the first element, that will be equal to 1 by the determinant of the Jacobian multiplied by y23 0, y31 0, y12 0, 0 x32 0 x13 0 x21 and x32 y23 x13 y31 x21 and y12. This is the B matrix for the first element, and I mentioned earlier that the determinant of the Jacobian will be 2 times the area of the element. So let us say if I take the sides, let us say this is 2 inches and this is 3 inches, and thickness of, if I say the thickness T is equal to 0.5 inches, okay, then the determinant of the Jacobian will be 6, and these values y23, I can get these values like this, y23, the y2 minus y3 for this node, y2, node number 2 is node 2, node number 3 is node 4, so y2 minus y3 will be 2, and similarly y1 minus y2, that is y1 minus y2 will be minus 2. Okay, and here I will get 0, minus 3, 0, 3, 0, 0, and then here I will get minus 3, 2, 3, 0, 0, minus 2. This will be the B matrix for the first element, and similarly for the second element. Would come out to be B for the second element would be 1 by 6 multiplied by minus 2, 0, 0, 0, 2, 0, 0, 3, 0, minus 3, 0, 0, and 3 minus 2 minus 3, 0, 0, 2. Okay, and once I have the B matrices, I can get the stiffness matrices by saying that, let's say, the stiffness matrix for the first element, that would be given by thickness multiplied by area multiplied by B transpose dB. Okay, where B transpose will be the transpose of this matrix, that will give me a 6 by 3 matrix. D will be a 3 by 3 matrix. Okay, and B is again a 3 by 6 matrix. So this whole thing is going to give me a 6 by 6 matrix. Okay, and okay, so this will be a 6 by 6 matrix, and these are the local node numbers, and if I look up my element 1, that is defined between nodes 1, 2 and 4. Okay, so the nodes are global node numbers will be 1, 2 and 4. So this way, in the global matrix these locations would occupy the locations 1, 2, 3, 4 and 7, 8. Okay, that is because corresponding to node number 1, the global locations will be 1 and 2. Corresponding to node number 2, the global locations would be 3 and 4, and corresponding to node number 4, the global locations will be 7 and 8. Okay, so when I make my global matrix, my global locations will be 1, 2, 3, 4, 7 and 8. Okay, that is because I have numbered them as 1, 2 and 4. Okay, and similarly when I consider my second element, that is stiffness matrix for the second element, that will again be a 6 by 6 matrix, and that is the second element is defined between locations 2, 3 and 4. So the global locations occupied will be 3, 4, 5, 6 and 7, 8. Okay, so this will go to global locations 3, 4, 5, 6, 7 and 8. Okay, and if I look at the boundary condition in this case, I have taken nodes 4 and 3 to be fixed, and node 1 is fixed in the y direction. Okay, so corresponding to that, my boundary condition will be Q2 will be equal to 0, because this is constrained in the y direction, it can move freely in the x direction. Okay, similarly, if I take node 3, that will give me Q5 will be equal to Q6 will be equal to 0, and corresponding to node 4 will get Q7 equal to Q8 equal to 0. Okay, and in my potential energy expression pi, this term Q is going to contain 8 terms, and K will be an 8 by 8 matrix. Okay, so this term K will be an 8 by 8 matrix, and in this 8 by 8 matrix my first element, okay, the first element will occupy these locations 1, 2, 3, 4 and 7 and 8. Okay, so 1, 2, 3, 4 and then 7 and 8. Similarly, in this direction 1, 2, 3, 4 and 7 and 8. So these locations will be occupied by elements of the first stiffness matrix, and the second stiffness matrix as 3, 4, 5, 6, 7, 8 locations will be occupied by the second stiffness matrix. So that will take locations, so 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8 and all these. Okay, so these are the locations of the second stiffness matrix, these are the locations of the first stiffness matrix, and this way we will get the global stiffness matrix. And as I mentioned, these are the boundary conditions we have. Okay, so to complete this potential energy expression, this minus Q transpose F. F will again contain 8 terms. Okay, and if I use the method of elimination, my Q2, Q5, Q6, Q7 and Q8 all 5 are constrained. So by the method of elimination, the equation that I finally get, they are of the form K prime, Q prime are equal to F prime. Okay, and K prime is obtained from K by deleting locations of the constrained nodes. Okay, so in this case 2, 5, 6, 7 and 8 are constrained. So that means 2, 5, 6, 7 and 8, all these locations, all these columns will get deleted, and similarly 2, 5, 6, 7 and 8, all these columns will also get deleted, all these rows will get deleted. So 2, 5, 6, 7, 8, 6, 7 and 8, all these will get deleted, and eventually we will get this 3 by 3 matrix as the K prime matrix. Okay, and Q prime will have the other 3 nodes, which will be Q prime will be equal to Q1, Q3 and Q4 transpose, that will be Q prime, and K prime will be a 3 by 3 matrix. And similarly F prime will also contain only 3 elements, which will be F1, F3 and F4. Okay, and this set of equations can be solved to find out the values of the Q's. Okay, this will give us 3 equations, 3 variables. We can solve them to get Q1, Q3 and Q4. And once we have that, then in order to compute the strains, we say epsilon, which is the strain, is equal to B times Q for each element. So for the first element it will look like this, and similarly for the second element we will get where Q1 is a displacement matrix for the first element, Q2 is for the second element, and so on. And for getting the stresses, sigma we'll say it will be equal to D times BQ, and we can get the strain and stresses in both the elements. Okay, so the only thing that changes in the case of 2D elements is how this global matrix is compiled. Okay, because now we'll have twice as many locations in the stiffness matrix as there are the number of nodes. If you have 4 nodes, there will be 8 locations. That's the only difference. Okay. Now this is as far as three noded triangular elements are concerned, and as far as the potential energy approach is concerned. If we quickly look at how to use the Galerkin's approach for the same element, that means if we have an element like a triangular element like this, okay, and we have said that its displacement matrix is given by q1, q2, q3 till q6. That is for this element, and the let's say the locations are given by x1 y1, x2 y2 and x3 y3. Okay, we have already mentioned that we will say x will be equal to n1 x1 plus n2 x2 plus n3 x3 and so on, and similarly y will be n1 y1 plus n2 y2 and so on. That we have already seen. Now when you are using the Galerkin's approach, we have to give a set of virtual displacement to this element. Okay, let's say the virtual displacements are given by psi 1, psi 2, psi 3, psi 4, psi 5 and psi 6. Okay, and we will define a virtual displacement vector which will be given by, let's say, psi, which is psi 1, psi 2 till psi 6 transpose. Okay, this is a virtual displacement vector for this element that gives a virtual displacement of the 6 degrees of freedom. Okay, and if we have a general 2D element like this consisting of a number of nodes, we will define a global vector which will be, let's say, psi global, which will consist of psi 1, psi 2 till psi 2n, where n is the number of nodes. Okay, this will be the global virtual displacement vector. Okay. Now coming back to this element, if you take any arbitrary point here and we want to find out the virtual displacement at this point. Okay, let's say the virtual displacement at this point is given by phi. Okay, phi x and phi y. Okay, so the virtual, if you look at the strain, okay, the strain at that point, or let's say if you look at the u vector, u first, we said u is equal to n times q. Okay, u is nothing but u v transpose, and we said this is equal to n times q. Okay, similarly if you look at the virtual displacement, that is phi, which is nothing but phi x phi y transpose, we will say that this will be equal to n times psi. Okay, what that means is we will say phi x is equal to n1 psi 1 plus n2 psi 3 plus n3 psi 5, and phi y will be equal to n1 psi 2 plus n2 psi 4 plus n3 psi 6. Okay, this is similar to the expression that we had for this expression. Okay, u equal to nq, the expression we had for deformations. They are virtual deformations, so the expression is going to be the same. Okay, and if you look at the expression for the internal virtual work done, internal virtual work, that is equal to the integral of sigma transpose multiplied by epsilon of phi multiplied by dV, where epsilon of phi is the strain that would be caused due to the virtual displacement. Okay, so we have said if u is equal to nq, then we can differentiate u and get an expression for epsilon, which is given by epsilon is equal to bq. Okay, similarly, if I contrast this with my relationship for phi is equal to n times psi. So epsilon of phi will be equal to b times psi. Okay, the steps involved in getting this matrix B would be the same as what we did yesterday for getting this matrix B. Okay, so epsilon of phi will be equal to b times psi. Okay, so if you look at this expression now, epsilon of phi will be b times psi, and sigma, so I say sigma will be equal to dbq. Okay, so sigma transpose will be q transpose b transpose into d. So I can put those expressions over here, and the internal virtual work done. Okay, the internal virtual work, I can get an expression for that, which is integral of sigma transpose epsilon phi dV, nothing but thickness of the element multiplied by dA. Okay, so this will be equal to the integral of q transpose b transpose d b psi into thickness into dA, and again q, b, d, b and psi and Te, all these are constants. Okay, so this will be equal to integral of dA will give me the area of the element. So finally I will get this to be equal to q transpose multiplied by Ke multiplied by psi. Okay, where Ke will be these three terms multiplied by Te into the area of the element. Okay, this is same as what we had when we are using the potential energy approach. Ke will be equal to Te into Ae multiplied by b transpose dB. Okay, so this is the expression for the internal virtual work done for an element. If you consider the internal virtual work done by the complete body, that will be equal to sigma q transpose Ke psi, and that will again assemble as global matrices and get q transpose K psi global. Okay, again the process of assembling the global matrices is the same as what we had earlier. Okay, and similarly if we look at the external virtual work, that we have said earlier, or we have shown earlier, as integral of phi transpose f T dA plus integral of phi transpose T into the thickness dl plus sigma phi I transpose Pi. And again we can show that this will be equal to psi transpose global multiplied by f. Okay, the process will again be the same. We'll put expressions for phi, we'll put expressions for f, carry out the integral, and we'll assemble these force matrices. Okay, so the Galerkin's approach will gives us that internal virtual work done is equal to the external virtual work done. Okay, so this will effectively give us an equation of the form Q transpose K psi global minus psi global transpose times F is equal to 0. Okay, this is the equation we will get by taking this and this together. Okay, the expressions for the stiffness matrix and for the force matrix and for Q will remain the same. Okay, and again when we look at this, we will say that this should be valid for all values of virtual work given, virtual displacement. Okay, since it has to be valid for all values of the virtual displacements, we will finally get the equation will be similar. Q transpose K minus F. Q transpose K will be equal to F. Okay, or KQ will be equal to F. And again we can use the same boundary conditions and solve these system of equations. Okay, so eventually whether we use the Galerkin's approach or the potential energy approach, will finally come down to the same expressions for the stiffness matrix and force matrices and the displacement matrices. Okay, the final equation that we will get, they will be the same, and the method of solving will also remain the same. Okay, any questions up to this point? Okay. And the next thing that we will take up in two-dimensional problems is the case of four-noded elements. If we have a four-noded quadrilateral elements, okay, that means our element looks like this. So we have 1, 2, 3 and 4. Okay, so we have 4 nodes, and the deformation of these 4 nodes okay, so the Q1 to Q8 will be the 8 deformations at these nodes, and the deformation vector for this element will be given by this 8 tuple okay, and the look x1 y1, the coordinates are x1 y1, x2 y2, x3 y3 and x4 y4. Okay, and now again, just like the elements earlier, we have to give 4 shape functions in order to get the deformation at any arbitrary point. Okay, so if you want to get the deformation in the x direction, we will say that the deformation in the x direction u will be equal to n1 q1 plus n2 q3 plus n3 q5 plus n4 q7, and v will be equal to n1 q2 plus n2 q4 plus n3 q6 plus n4 q8. Okay, where n1, n2, n3, n4 are the 4 shape functions. Okay, so if you consider n1, we want n1 to be equal to, you want n1 to be equal to 1 at node 1 and it should be 0 at all the other 3 nodes. Similarly, n2 should be 1 at node 2 and should be 0 at all the other 3 nodes, and so on. Okay, and so we will say n1 is equal to 1 at node 1 and 0 at nodes 2, 3 and 4. Similarly for the other nodes. Okay. In order to formulate these shape functions, what we will do is we will define two parameters, zeta and eta. Okay. And we will say that, let us say along this direction from 1 to 2, zeta, let us say at this point zeta will be equal to minus 1 and here zeta will be equal to plus 1. Similarly in this direction we will say eta will be equal to minus 1 and here we will say eta will be equal to plus 1. Okay, so along this edge eta is minus 1 and along this edge eta is plus 1, and similarly along this edge zeta is minus 1 and along this edge zeta is plus 1. So this is in some sense a local coordinate system that we have defined. Okay, and if we look at this local coordinate system, then n1 has to be 1 at node 1. Okay, that means at zeta and eta values of minus 1 and minus 1, n1 should be 1 and it should be 0 at all the other 3 nodes. If I consider this line and this line, okay, this line has an equation given by zeta equal to 1, okay, and this line has an equation given by eta equal to 1. Okay, so a term of the form 1 minus zeta into 1 minus eta will be 0 along this edge as well as along this edge. Okay, that means it will be 0 here, here as well as here. Okay, so if we say n1 will be some constant multiplied by 1 minus zeta into 1 minus eta. Okay, then n1 has to be 0 at all these 3 nodes. Okay, it has to be 0 along this edge as well as along this edge. Okay, and to get this value of C, we will again use the fact that at node 1 n1 has to be equal to 1. Okay, if n1 has to be 1 at this node, that means at this node zeta is equal to minus 1 and eta is equal to minus 1. Okay, so we will put these values over here. We will get 1 will be equal to C multiplied by 2 into 2, which is 4. So we will get C to be equal to 1 by 4. Okay, or we will get n1 to be equal to 1/4 of 1 minus zeta multiplied by 1 minus eta. Okay, this is a shape function we will choose for n1. Is that okay? Similarly, if we take n2, okay, and n2 has to be 1 at node 1, okay, it has to be 0 at all these 3 nodes. So along this edge as well as along this edge it has to be 0. Okay, and the equation of this edge is zeta equal to minus 1. Okay, so for n2 we will say it will be of the form some constant multiplied by 1 plus zeta into 1 minus eta. Okay, and at zeta equal to 1 and eta equal to minus 1, n2 is equal to 1. We will use this condition now. Okay, and we will get n2 to be equal to 1/4 of 1 plus zeta multiplied by 1 minus eta, and similarly we can get n3 and n4. n3 will be 1/4 of 1 plus zeta into 1 plus eta, and n4 will be 1/4 of 1 minus zeta into 1 plus eta. Okay, we will get the 4 shape functions like this. Okay, and once we have the 4 shape functions, we can then write expressions for u as n1 q1 plus n2 q3 and so on, and similarly v will be equal to n1 q2 plus n2 q4 plus and so on. Okay, so where n1, n2, n3, n4 are given by these expressions, and similarly for n1. Okay, or we can write this in a matrix form as u equal to nq, where n will be n1 0, n2 0, n3 0, n4 0, 0 n1, 0 n2, okay, and q is equal to q1 q2 till q8. Okay, and again we'll choose an isoparametric representation. We'll say x will be equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4, and y will be equal to n1 y1 plus n2 y2 plus n3 y3 plus n4 y4. Okay, where n1, n2, n3, n4 are the four shape functions in terms of zeta and eta, and x and y are given by these relations, u and v are given by this relation. Okay, so this way we have formulated the basic equations for relating the deformations and the position vectors. Okay, and now again to get the strains, that is epsilons, we need expressions for del u by del x and del u by del y. Okay, and this we derived last time that this is equal to Jacobian inverse multiplied by del u by del zeta and del u by del x, and del u by del eta. Okay, where the Jacobian is Jacobian is given by del x by del zeta, del y by del zeta, del x by del eta, and del y by del eta. Okay, and in order to find expressions for del u by del x, I now need to find out del u by del zeta, del u by del eta, and these four terms. Okay, if I try to get del x by del zeta, that is this first term, I will have to take this equation and differentiate it with respect to zeta. Okay, and all n1, n2, n3 and n4 will have terms of zeta in it. Okay, so del x by del zeta will come out to be minus of 1 minus eta times x1 plus 1 minus eta times x2 plus 1 plus eta times x3 minus 1 minus eta times x4. This will be the expression for del x by del zeta. Similarly, del x by del eta will also be an expression like this, and so on. Okay, and after getting all these expressions here, I can finally come up with an expression for epsilon which is equal to b times q. Okay, but now B, this matrix B will contain expressions of zeta and eta. Okay, B is not going to be a constant matrix. Okay, so B will contain expressions of zeta as well as eta. Okay, and if I use this expression and try to get the expression for the strain energy, that is UE, which is given by integral of half sigma transpose epsilon dV, this will be equal to TE by 2 TE into dA will be dV, and sigma transpose will give me Q transpose B transpose D, epsilon is B times Q, so B times Q. Okay, and again in this expression Q transpose is a constant, Q is a constant, but B transpose and B, they are not constants, they are functions of zeta and eta. Okay, so in order to evaluate this integral, okay, this will become TE by 2 into Q transpose into integral of B transpose dB dA, okay, this whole thing multiplied by Q. Okay, so let's say I'll take TE inside, and what we'll do is we'll call this matrix, this thing multiplied by TE, as our stiffness matrix. Okay, so this will be equal to half of Q transpose KE multiplied by Q, where KE will be equal to TE into the integral of B transpose dB dA. Okay, and for finding out this stiffness matrix, one has to carry out this integral. Okay, because B consists of terms of zeta and eta, and dA, the differential area, which will also consist of terms of zeta and eta. In fact, we can show that dA will be equal to mod J multiplied by d zeta d eta. Okay, so this determinant of J will again have terms of zeta and eta. Okay, so this integral will contain terms of zeta and eta, and the stiffness matrix can only be computed by carrying out this integral using numerical techniques. Okay, so for finding out the stiffness matrix in the case of a 4-noded element, one has to carry out this integral using numerical techniques, and only then we can get the values of the stiffness matrix. Okay, but the final equation that we get will remain the same. We have got the stiffness matrix for the element, and then when we consider the total strain energy in the body, that will be equal to sigma of half Q transpose KEQ, which will again be equal to half of Q transpose KQ. So final equation will remain the same, but for finding out the stiffness matrix, one will have to use a process of integration. Okay, without using this, without carrying out this integral, one cannot find out the stiffness matrix. Okay, so unlike our 3-noded elements and all our one-dimensional elements, in this case for finding out the stiffness matrix, we have to carry out this integration. Okay, and this integral is going to be quite complex, because we will have the term of Jacobian, which also contains zeta and eta, and B transpose, they also contain terms in zeta and eta. Okay, so the whole thing is going to be quite complex. Okay, any questions up to this point?
So are we supposed to solve this integration?
The program is supposed to do it. Whichever finite element program you are using, the moment you use a 4-noded quadrilateral element, it will solve this integral to get the stiffness matrices. Okay, it cannot be solved by hand. Okay, and similarly, when we combine the force terms, the body force terms, that is the potential energy contribution due to the body forces. Okay, U transpose is NQ. Okay, so we have U equal to NQ, so U transpose will be Q transpose N, and Q transpose into N transpose. So this will be equal to integral of Q transpose N transpose F into the thickness into dA. Okay, Q transpose is of course a constant, but N transpose is not a constant, that has terms of zeta and eta in it. Okay, so this is equal to Q transpose into TE into integral of N transpose F dA. Okay, so this is equal to, we will say, Q transpose into FE, where FE is the body force vector for the element body force vector. But again Fe is computed after computing this, carrying out this integral. Unless we carry out this integral, we cannot compute Fe. Okay, so in the case of a 4-noded element, we have to compute this integral to find out the body forces, the effective body force acting at the 4 nodes. Okay, similarly, the attractive force, that will also have to be split into the 4 nodes by carrying out an integral. Again, eventually we will combine all these to get an equation of the form half of Q transpose KQ minus Q transpose F. Okay, but the process of finding out this F and this K will involve numerical techniques. Okay, we will have to solve complex integrals. Okay, any questions up to this point? Essentially, this equation remains the same. The process of solving this is the expression for pi. Okay, this expression remains the same, and the process of solving it will also remain the same. But what changes is your shape functions and the process of computing K and F. Okay, we will see as elements become more and more complex, finding out these K and F matrices, the process of finding that out also becomes more and more complex. Okay, any question up to this point? Okay, that way we will stop here. The next time we will see some more elements and then we will go on to 3-dimensional problems.